Hi, my name is Zvonimir Pavlinovic, and today I'll present work on data flow refinement type inference algorithms. This is joint work with Yusen and Thomas Wies. Our work is centered around type systems that attempt to improve over classical type systems such as Hindley-Milner by inferring global invariants of higher order programs using the notion of refinements over classical base types. An example of such systems are liquid types that infer global data flow invariants of functional programs as predicate abstraction implemented as horn clause solving. Here, type refinements are finite conjunctions over decidable predicates. Suppose we want to prove that Fibonacci function is increasing with a set of predicates that allow comparing integer variables to each other and against number 2. Liquid type inference fails to prove that Fibonacci is increasing with this set of predicates. For instance, the following type encoding increasiveness is not inductive. If x is 2, then by induction we can only know that the then branch is greater or equal to 1. What we need here is a richer domain, so we can extend the set of predicates by allowing comparing an integer variable to 1. Then, the following type becomes inductive. Liquid types mine predicates from program syntax and allow users to specify them, but knowing in advance the set of necessary predicates is really hard. What if we need infinite domains of refinements such as polyhedra? How will we obtain type inference over such domains? Further, what if even this is not enough? Consider the following program where we have g that multiplies input integer with 2, h that multiplies input with -2, and the classical apply function. The main function then applies g to a non-negative integer input and h to a negative input, thus always producing a positive number. Regardless of the domain of type refinements, we would fail to verify that v is greater or equal to 0. Both g and h flow to f, and both non-negative and negative z flow to x, a flow of data also described in earlier work. The inference of the apply does not distinguish between two applications of g and h. That is, the inference of apply is not aware that g should be applied to non-negative integers and h should be applied to negative integers. So the inference concludes that input f to apply can be called and produce any integer, which is not sufficient to prove that v is non-negative. Drift gets around this problem by allowing typing the apply function based on different calling contexts. If we define these calling contexts as locations where the call to apply happens, in this case I and k, the inference of apply can associate g to non-negative inputs and h to negative inputs. One thing to notice here is that apply is typed based on how it is used in the program. The assigned type does not model the complete behavior on all possible inputs, yet only on those actually reachable in the program. This is one of the distinguishing features of data flow refinement type inference algorithms. The main challenge and problem in this work is to systematically construct data flow refinement type inference algorithms that terminate, support both infinite and finite domains of type refinements, support context sensitivity, and do not require the user to create or argue the soundness of typing rules and the type inference algorithm. The main contribution of our work is Drift, an abstract interpretation-based framework for systematically constructing data flow refinement type inference algorithms. In Drift, a type system designer is only responsible for providing the definitions for base types, domain of type refinements, and method for inferring shapes of refinement types. The designer also provides the desired level of context sensitivity in terms of finite call size tags that are used to type functions separately based on different calling contexts. Drift then produces a type system with typing rules and the inference algorithm that infers data flow properties of higher order programs and is sound by construction. Drift relies on abstract interpretation, a framework for systematic construction of static analysis by successive over-approximations of concrete program semantics. Our work was inspired by earlier work by Patrick showing that modular type inference algorithms such as Hindley-Milner can be seen as static analysis over approximating the notational semantics of functional programs. In our work, though, we have to start from a different concrete semantics, as follows. We need a concrete semantics that is both structural and captures data flow properties of higher order programs. The latter is needed as that is what, say, liquid types intuitively abstract. The former is needed so we can connect it easier to the typing rules that are structural. The issue with the notational semantics is that, although structural, is also modular. For instance, for the case of recursive functions, the denotational semantics assigns meaning to the function for all possible inputs, not only on those actually reachable in the enclosing program. The operational semantics is, on the other hand, not completely structural. In the application rule for function application, the actual function being called is not necessarily a sub-expression of the whole function application expression. We solve this issue by devising a novel concrete data flow semantics of higher order programs. We intuitively explain our concrete semantics by comparing it to the big step operational semantics. Suppose that E1 in function application evaluates to some lambda on some execution path. Similarly, assume that E2 evaluates to 1 on another execution path. Suppose then that the big step operational semantics evaluates the body of lambda to 2 with 1 as input x. We hence have 2 as the result of the application and the computation continues. In our semantics, on the path the lambda takes to E1, we assign an empty table to each element of the path. The tables model functions, that is, how functions are used at different call sites. Initially, all the tables are empty as the lambda has not yet been called. Our semantics then evaluates E2 to 1 and assigns 1 to each element of execution path to E2. In the next step, our semantics stores 1 as the input for the table at E1 for the current call site colored in red. What happens next is that this input 1 flows to the lambda definition by means of exchange, that is, propagation of data between tables at the execution path of the lambda. We call this function prop. Inputs are flowing in the direction of call sites to function definition. Now that we have 1 as the input at a current call site propagated back to the lambda, we can similarly evaluate the lambda body. As before, the result of evaluation is 2, now stored as the output for the current call site in the table associated with the lambda. Now, we propagate that output back in the other direction, again using prop. The outputs are flowing back in the opposite direction. This change of direction in data flow for tables intuitively corresponds to the change of variance in function subtyping at a type level. Once the output 2 has reached the table associated with E1, we can return 2 as the result of function application and continue in the same fashion. Here is an illustration of the computation carried by our semantics on an illustrative program where we have function f that simply calls itself recursively with an ever-decreasing input stopping at 1. We then call f with 2 and 0, the latter call being non-terminating, which we model with bottom. In our semantics, f takes 2 execution paths leading up to the 2 calls. At each element in these paths, we store tables ultimately describing how f is used at those paths, and those paths only. For instance, table at f in f applied to 2 will remember input-output behavior for that call only, and similarly for the other call. The table corresponding to the definition of f contains information for both call sites. As a matter of fact, since f applied to 2 induces a call f applied to 1, The table will actually also have an entry for that recursive call as well. Let us also describe how the results computed by our semantics look like for higher order programs. In the current program, we have a function f that calls an input function g with 1. We then imply h with g1, which is a constant 0 function, and g2, which is identity. Let's look how the table for h looks like. As expected, it is a nested table. Let's focus on the call to h with g1 that happens at location c. We thus have an entry in h indexed by c. The entry is pair of a table and 0, the latter being the result of the call of h to g1. The nested table has one entry index with ac, which represents the call stack. We have a call at location a induced by call at location c. The input at the nested call is 1 and the output is 0. Indeed, g1 applied to 1 gives 0 as the result, which is then propagated back as the result of h applied to g1. Let's look formally how we define our concrete semantics. We model each execution step as a node. We have expression nodes that represent evaluation point of an expression at a given location under the current environment. We also have variable nodes that represent the execution point of binding a value to an input variable. Variable nodes are modeled using again the current environment, the input variable itself, and the call stack to uniquely represent the current evaluation of function body. Stacks are modeled as sequences of call locations inducing the current call. Environments map variables to corresponding variable nodes. Data flow values are non-terminating bottom, arrows denoted as omega, constants, and tables modeling functions by remembering input-output value for every call side stack. The ultimate product of our semantics is an execution map from execution nodes to data flow values. The concrete transformer for our semantics is a function step that evaluates an expression in the current environment, stack, and execution map, producing an updated execution map. The transformer is purely structural and defined over the previously introduced propagation function prop. The actual concrete semantics takes the input program and updates the initially empty map in a fixed point fashion until no more updates, that is, no more data flow occurs. Let us now explain how data flow propagation works more formally. The propagation function prop is applied between two values at successive execution nodes. Constants are propagated forwards using joins. In practice, v is here bottom, so we merely push the constant to the next execution node. Tables are already more interesting case. For every call side stack S, we first propagate values between their inputs in the backwards direction. The propagation for output values goes in the other direction. The updated input and output values are finally stored back to the tables. Here is an example of a concrete transformer for the function application. We use A, B, and C superscripts to designate locations of the sub-expressions. We are evaluating the function application with the current environment E, call side stack S, and the execution map M. We first evaluate E1 and get an updated map M1 as well as the table V1 stored at execution node EA, corresponding to the current evaluation of E1. We do similarly for E2. We then exchange information between input V2 and the input value stored in the table for the call side stack AS. Similar exchange is happening between the output in the table for that call side stack and the result of the function application. Finally, the updated values are stored back obtaining a new map. Observe how the concrete transformer is purely structural. Let us describe abstract semantics that we build on top of the concrete semantics. The relational semantic replaces concrete values with relations, modeling how the concrete values relate to their environments. Collapse semantics further abstracts concrete stacks with user-provided finite abstract stacks, thus collapsing tables. Finally, parametric refinement type semantics abstracts concrete relations with base types in user-provided refinement domain. The user also provides shape widening to allow terminating inference of refinement type shapes, an example being Hindley-Milne algorithm. Tables are effectively replaced with function types indexed by each abstract call side stack. Let us take a closer look at the relational data flow semantics through our earlier higher-order program. Let's consider the table for age. First, we introduce a dependency variable x for the table so we can relate function outputs to inputs. Let's now look at the entry for singleton call stack C. The input is a nested table we describe shortly. The output is a relation with a single row encoding that the actual output value is 0, denoted with the familiar notation nu. We also explicitly model that the input x related to that output is a function, denoted here with capital F. We don't model precisely dependencies on function values, similar to liquid types. Now let's take a closer look for the nested table. Again, we introduce a dependency variable, here y. The input to the nested table is singleton relation encoding that the actual input value is 1. The output is a relation abstractly connecting that input to the output value 0. Let us take a closer look at a collapsed data flow semantics example. Suppose we want to have a context-insensitive analysis, similar to liquid types. The set of abstract call side stacks then has only one generic stack, which we can disregard. We can also remove the square bracket notation since there is only one entry in the table. Since we don't distinguish any more inputs to H based on different call side stacks, we have table entries of the relational semantics joined together. First, the output of H is a relation encoding the information that the output value can be either 0 or 1. The input to H is again a collapsed nested table that has 1 as input and both 0 and 1 as output. In parametric semantics, again, the user provides the notion of base types and the abstract domain of type refinements. The domain can be finite or infinite. In the latter case, the widening that comes with the domain ensures the semantics, that is, the inference is terminating. The user also provides shape widening, a mechanism for terminating inference of refinement type shapes. We'll mention an example shortly. Once such shapes are inferred, base type and refinement domains abstract the concrete relations. Here are the typing rules for our parametric semantics. They precisely characterize the fixed point of the semantics. For instance, the fixed point will satisfy the typing rules. The typing rules resemble the typing rules in, say, liquid types. The difference here is that we abstract over the domain of type refinements and we also add support for context sensitivity. Let us focus on the rule for typing functions. We type the function for each abstract call stack. We then, as usual, extend the typing environment, type the function body, and then make sure that classical subtyping requirement holds for the type of the whole function, here restricted to the current abstract call stack, the restriction being denoted using the bar notation. Liquid types are a particular instance of our parametric semantics. Shape widening and inference of base types is done by first calling Hindley-Milne type inference. The refinement domain is a finite conjunction of chosen decidable predicates. This domain is of finite height, so no widening is really needed. Technically, join can be used as widening. Liquid types are not context sensitive. So what happens is that execution nodes are in one-to-one correspondence with the program locations. We have implemented drift in OCaml on top of Apron library for numerical abstract domains. We aimed at evaluating drift over 250 programs used in related work that involve both first-order and higher-order programs. We wanted to measure how much the richer abstract domains and context sensitivity help. Also, we wish to compare drift to the state-of-the-art tools. We instantiate our framework with both octagon and polyhedral abstract domains without context sensitivity and with one context sensitivity, the latter defined as abstract call site stacks of length 1. The polyhedral domain we use here is polka, convex polyhedra with linear equalities. Loose polka here means that the domain captures only loose inequalities, and strict means that the domain captures strict inequalities only. For each domain, we also use widening with and without thresholds, respectively denoted with W and TW. The benchmarks involve first-order programs, higher-order programs, and programs involving arrays, lists, as well as errors. For both context-insensitive and context-sensitive configurations, we can see that richer abstract domains help. For instance, Polka can verify more programs than octagons, but naturally take more time. Further, context sensitivity also helps. For instance, context-insensitive loose Polka with threshold widening can verify 217 programs, while the context-sensitive version can verify 244 programs. In the next experiment, we compare drift to state-of-the-art tools. In particular, we compare one context-sensitive, loose Polka with threshold widening instantiation of drift to R-type, dsolve, and Mochi-related tools. Our tool performs favorably compared to the state-of-the-art tools. Drift can verify more programs in total. We here highlight the benchmark subsets for which drift performs the best in terms of the number of verified programs. We use dashes to denote timeouts, which were capped at 5 minutes. In summary, we introduced drift, a general abstract interpretation-based framework for systematically constructing sophisticated data flow refinement type inference algorithms that allow arbitrary abstract domains of type refinements, such as octagons and polyhedra, allow different notions of call site context sensitivity, and introduce a novel data flow concrete semantics for higher order programs. We have implemented and evaluated drift using octagon and polyhedra abstract domains and show that our tool performs favorably over the state-of-the-art tools. Thank you.